Okay, let's unpack this. Imagine you're up there, soaring high. Everything seems perfectly normal. Then suddenly, boom, an emergency hits. Your fancy flight management computer, your radar, all offline, gone.
Yeah.
You're not even totally sure where you are, just, a rough idea. Maybe within 30, 50 nautical miles of somewhere you could land. What do you actually do?
It's intense.
This isn't just some hypothetical, Reg. This is a pilot's absolute nightmare scenario.
Yeah. And it's fascinating, really, how quickly everything can just strip back to the absolute fundamentals when the tech fails you.
Right.
So in this deck dive, we're peeling back the layers on a very specific but incredibly important aviation challenge, executing what's called a raw data non-precision approach, an NPA.
Okay.
We'll specifically focus on a VOR approach coming in from an overhead pattern. We're drawing heavily from Captain Ashutosh Chopra's Commercial Pilot's Handbook for this.
Good source.
Definitely. And this isn't just about, flying the plane. It's really about maintaining that critical spatial orientation, the manual piloting skills, things that are still vital, even with all the automation we have today.
Exactly. And maybe for folks listening, when you say raw data, what does that really mean? Why is it so different?
Think of it like flying by feel, almost, by just the basic instruments.
Not the integrated map display showing you the way.
Precisely. You're looking at needles, dials, the most basic information. You're not relying on the flight management computer, the FMC, to plot your path. You are the computer, essentially.
Ah, okay.
You have to translate those basic inputs, direction from the VOR, altitude, maybe distance from DME, into, a 3D mental picture of where you are and where you need to go.
So this deep dive is really going to highlight the sheer precision needed, the anticipation.
And the mental agility, absolutely. It's what pilots need to navigate and land safely when all those smart systems, they're just out of the picture.
And I think the handbook also touches on other types, right? Like NDB approaches. How do they fit in?
Yeah, it does mention them. And it's a good comparison because it shows the spectrum, even within raw data. A VOR, that's VHF omnidirectional range, usually gives you a nice steady needle, a deviation bar, often distance measuring equipment, DME, for your miles.
Yeah.
An NDB, a non-directional beacon, that's even more basic.
That's information.
Much less. No steady deviation bar like a VOR. No co-located DME usually. You're relying much more on precise timing, your magnetic compass getting configured really early.
So more challenging in some ways.
It just emphasizes the adaptability required, Even when you're already down to basic flying, there are still levels to it.
Okay, so let's jump into that scenario from the handbook.
Yeah.
We've got this pilot distressed, maybe 30 to 50 miles out from an airfield. Let's call it ABCD.
Right.
It's got a single runway served by a VOR approach from overhead. All the fancy stuff is down. What's the absolute first thing they need to do? Just even find the airfield.
First things first, you got to tune the VOR frequency for ABCD. Tune and identify.
Make sure it's the right station.
Exactly. You can see it on your EFIS, your digital displays, or listen to the Morse code identifier on the nav radio panel. Critically, the handbook says, select VOR on the EFIS and switch the map display to center mode.
Center mode. Why is that important?
Think of it like your car GPS map, where your car icon stays in the middle.
Okay, yeah.
It means you can always see things all around you, including that VOR needle, no matter which way it's pointing. If you were in expanded mode and the needle was pointing behind you, you might just not see it on the screen.
Ah, okay. Critical information. Hidden.
Yep. So center mode keeps that vital needle visible.
Okay, so you see the needle pointing towards the airfield. You note the heading, turn the shortest way to match it. Then the book mentions aligning the course pointer. But carefully. Why?
Yeah. You align the course pointer, or OBS, to the same heading you're currently flying towards the VOR. It's vital.
Why? What happens if you mess that up?
You risk what's called a 180-degree error. Ambiguity.
Right.
If you just blindly set the course without checking your heading to the station, you might accidentally select the reciprocal, the opposite direction. The deviation bar might even look centered, fooling you.
But you'd be flying away from the VOR.
Exactly. Flying directly away from where you want to go. So it's a crucial cross-check right at the start. Make sure your instruments are telling the truth about your direction towards the station.
Wow. Okay. So, simple step, huge consequences if missed. You're heading towards the VOR now. You see the DME distance clicking down. Time to think about descent, right? The handbook gives some rules of thumb.
It does. This is where the mental math starts kicking in. The guideline is, if you're overhead the field and on the outbound leg of the holding pattern you're about to enter, you're generally okay if you're at or below 7,000 feet. above ground level, AGL.
Okay, 7,000 AGL.
And in a typical holding pattern, a full racetrack circuit, you can expect to lose about 4,000 feet pretty comfortably.
Add those up.
You're looking at being able to descend roughly 11,000 feet within that whole maneuver, from being overhead initially to completing one hold.
So you do a quick calculation. Current altitude minus 11,000 feet. Does that roughly match the distance?
Yeah.
I still have to go.
Pretty much. If you have way more altitude than that, you need to start planning how to lose it safely, maybe using speed brakes, maybe extending the hold.
And while all this is happening, you're probably also trying to deal with whatever emergency checklists are pending.
Oh, absolutely. You'd be running through things like the FMC failure checklist, maybe calculating your ref, your landing speed, or your go-around power settings.
Busy time.
Very. It's all about prioritizing, keeping that core task of navigating and managing the descent front and center, while also handling the emergency procedures.
Okay, so airfield located, descent plan roughed out.
Mm-hmm.
Now you need to actually enter the holding pattern safely. What's the challenge there? Why is knowing your position so stressed?
Well, entering a hold isn't just flying in circles. It's about maneuvering precisely into this predefined box in the sky. You're dealing with wind, the clock. You need to maintain separation from terrain and other traffic.
Right.
So the handbook emphasizes knowing your rough position relative to the approach chart and your current heading to the VOR. That tells you which type of entry procedure to use: direct, teardrop, or parallel.
Even though it's an emergency, you can't just, aim straight for the outbound leg?
You could, but joining the hold correctly ensures you stay within that protected airspace designed for the procedure. It's the safer, more structured way to do it.
Makes sense. And to help stay within that pattern airspace, the book suggests slowing down just before you get overhead the VOR to flap 5 speed. What does that mean practically?
Yeah, flap 5 speed means you extend the first notch of flaps.
Okay.
This does two main things. It slows the aircraft down, which gives you much better maneuverability within the tight confines of the holding pattern. And slower speed means a smaller turn radius, helping you stay well within the protected airspace limits.
Especially if the radials aren't perfect 90-degree corners out there.
Exactly. Real-world factors matter. Slower speed gives you more time to think, more margin for error. It's a key safety measure.
So you fly over the VOR, execute your entry procedure, and roll out onto the outbound leg of the hold. You start timing for 1 minute, typically. But the book adds a detail about timing if you did a direct turn outbound. Something about a beam the VOR.
Right. Abeam the VOR just means the point where the VOR station is directly off your wingtip 90 degrees to your side.
Okay.
If you made a direct turn outbound from overhead, you only start your 1 minute timer when you hit that abeam point. That marks the true start of the outbound leg relative to the VOR's position.
Got it. And this outbound leg, this is where wind really starts to matter, doesn't it?
Hugely. You have to apply wind correction. The rule of thumb is maybe 3 degrees of correction for every 10 knots of crosswind component. And you adjust your timing to shorten the leg for a tailwind, lengthen it for a headwind.
So it's not just fly heading, wait a minute, turn. It's constant calculation.
Constant mental calculation and adjustment. You're compensating for drift the whole time.
This sounds like where that spatial orientation becomes absolutely critical. The handbook warns that getting displaced laterally in the pattern, that can really mess up how you intercept the inbound course. It talks about building a mental picture.
It does. It means you're constantly visualizing, where is my aircraft in 3D space relative to that VOR, relative to the track I want to be on. You're picturing what the instruments should look like just before you start your turn inbound, as you roll out.
Anticipation.
Yes, you need to anticipate how that VOR needle is going to move as you turn. If your mental picture, your anticipation is off, you won't roll out correctly onto that inbound radial. You might overshoot, undershoot,
and end up outside protected airspace or just unable to get stable on the approach.
Exactly.
What if that happens? The source says the geometry is disturbed. The needle isn't where you expect it when you're rolling out on your intercept heading. What's the fix?
If things aren't lining up, if that mental picture doesn't match the instruments, you got to act fast. You might need to abandon the intercept for a moment and just head directly toward the VOR again to reorient yourself.
Sort of reset the picture.
Kind of. Or, if you have the fuel and time, maybe even fly another full holding pattern to get properly established before trying the inbound intercept again. The main goal is to capture that inbound radial cleanly as early as possible to set yourself up for a stable approach.
Okay, so let's say you nail the intercept, capture the inbound radial heading towards the VOR, you're decelerating to flap 5 speed if you weren't already there. Then as you get close, maybe 2 miles out, you set your course selector to the outbound radial for the next leg of the approach.
Correct. Preparing for the procedure turn or the outbound leg before the final approach.
And here the handbook introduces a really interesting correction technique. If, when you're flying towards the VOR, the needle isn't showing the reciprocal of your desired outbound course, you turn towards the needle by twice the error. A 2x correction. Why so aggressive?
That 2x correction is, it's a fundamental technique in raw data flying. It seems aggressive, but remember, the instruments have lag. The needle tells you where you were a moment ago, not where you are right now. So you need that sharper, almost overcorrection to get back onto the desired track quickly and efficiently. It stops you from sort of chasing the needle across the sky. It's about getting ahead of the aircraft again.
Anticipatory piloting again.
Exactly. So, for example, if your outbound radial is supposed to be 060, you're heading towards the VOR, and the needle should read 240, the reciprocal, but it actually reads 230. That's a 10-degree error to the left.
Okay.
You turn right towards the needle reading of 240 by twice the error, so 20 degrees. That helps you intercept that desired 060 outbound radial much more precisely when you pass over the VOR and turn outbound.
Fascinating. So you're not just reacting, you're actively correcting based on predicted instrument behavior.
Yeah.
Okay, so you're established outbound, descending according to the approach chart. Now you're heading towards the point where you'll turn back inbound for the final approach.
Right. Maybe a procedure turn, maybe just lining up for the final segment.
And about 2 miles before that turn-in point, you set your course selector to the final approach course. You plan your turn, usually aiming for a 45-degree intercept angle onto that final track. Why 45 degrees specifically?
That 45-degree intercept is pretty standard. It gives you a manageable rate of closure onto the final approach course. But the key is intercepting it promptly. Any delay means you can't start your final descent on time.
Which is critical for a stable approach.
Absolutely critical. The workload on a non-precision approach is high. You're constantly cross-checking altitude against distance, managing the descent. You need to be established on that final track as planned.
And if things have gone a bit sideways due to wind or something, and that 45-degree intercept isn't closing the deal fast enough, the handbook even suggests a 3x correction here. Even more aggressive.
Yes, potentially. Because capturing that final approach course now is paramount. Everything else depends on it starting your descent at the final approach fix, FAF, configuring for landing.
So you might need an even sharper turn initially.
You might need to momentarily increase your intercept angle, maybe turn more aggressively towards the course just to get that needle moving back towards the center quickly. Get it within maybe 10 degrees or so. Then you can shallow the intercept back to 45 degrees to capture it smoothly. The 3x idea emphasizes getting established decisively.
Okay, so the aim is hit that final approach fix altitude, the FAF altitude, as early as you can, maybe 5 miles out. You set your derived decision altitude in the altitude alert.
That's your minimum descent altitude plus a 50-foot buffer, typically.
Right, and make sure the final approach course is captured. Then what's the sequence?
Sequence becomes pretty critical. Typically around 2 miles from the FAF, gear down, select flap 15.
Slowing down more?
Yep. More drag, more lift. Then about 1 mile from the FAF, select your final landing flap setting, call for the landing checklist. You actually start your descent about 0.3 miles before the FAF to ensure a smooth transition onto the final descent path.
And the other pilot is busy too.
Oh yeah. They should be calling out DME distances and the altitudes you should be crossing at those distances based on the approach chart. Constant cross-check. 5 miles should be 2,000 feet. 4 miles should be 1,600 feet. That kind of thing.
Like a human altitude distance checker.
Pretty much. Essential backup.
What if you find yourself a bit high or low early on in that final descent? How do you adjust?
You can adjust your rate of descent. Again, sort of a twice the error guideline can work. If you're, say, 50 feet high and your target descent rate was 800 feet per minute, maybe increase it slightly to 900 for a bit to get back on profile.
So it's a very active process of managing that descent path.
Very dynamic. You're essentially creating your own glide path based on distance and altitude checks and constantly adjusting to stay on it. And importantly, remember, non-precision approaches don't always line up perfectly with the runway centerline.
Right. The VOR station might be off to the side.
Exactly. So the final approach course might be angled slightly towards the runway. It's designed to cross the extended center line at a point where, if you're at your minimum descent altitude, MDA, you're in a position to see the runway and land.
Which means if you are a bit high when you reach your decision altitude, You might need to look further sideways almost to spot the runway threshold.
That's possible, yeah. It's not always straight ahead like an ILS precision approach. Another element of spatial awareness needed right at the critical moment.
And this really circles back to the core lesson, doesn't it? The handbook stresses that even if you are flying this approach using the FMC, using LNAVM AV guidance,
which provides lateral and vertical paths,
you should still be monitoring the raw data backups.
Yeah.
The VOR needle, the DME, cross-checking everything as if you were flying it manually.
Absolutely. Because that preparedness, that constant monitoring, allows you to revert seamlessly to raw data flying if the automation fails at any point during the approach, which can happen.
So wrapping this up, what does this incredibly detailed procedure mean for you listening, whether you fly planes or just navigate complex decisions day to day?
Well, I think this whole deep dive into a raw data NPA, specifically this VOR example, just hammers home the importance of those foundational skills, that spatial orientation.
Right.
Even with amazing automation, being able to interpret the basic raw data, whatever that looks like in your field, and mentally simulate your position, your situation. That's often what saves the day when things go wrong.
Yeah. And the source material itself gives that stark warning, doesn't it?
Yeah.
Over-reliance on automation also slowly erodes our spatial orientation skills.
It's a powerful reminder. Technology is fantastic, offers incredible convenience and capability, but that deep understanding, the real ability to adapt, that comes from mastering the fundamentals.
And that recommendation to visualize the above during armchair flying.
It's not just for pilots. It's a universal idea for mastering any complex skill. Practice it mentally. Visualize the steps, the challenges, the decisions. Internalize it. Don't just memorize a checklist.
It really is about being well-informed, isn't it? Not just knowing what a system can do, but knowing what you have to do when the system can't.
Mm-hmm.
This whole procedure, I mean, from just finding the airfield with one VOR needle to managing all those precise turns, descents, corrections, it demands so much anticipation, so much active problem solving.
It really does. It's beyond just following steps. It's a testament to human adaptability, really.
So maybe the final thought for you to chew on is this. How do you prepare for that moment when your best tools fail?
Yeah, when you have to rely purely on your fundamental understanding, your own spatial awareness, whatever that means in your context. What are those raw data skills you're cultivating right now in your own life, your own work?
Skills that ensure you can navigate the unexpected, even when the automation, the usual safety nets just aren't there.